Okay, folks, lecture number 21. You can hear, right? Okay, let me know if you cannot hear me. We will begin with announcements. First announcement is that Project 3 is done. And that was a huge project for an introductory CS course, so congratulations to you all. Awesome work. There's always more to do. Part of that is homework 6, which is due on Monday. There will be a Gorilla section over the weekend that will cover mostly linked lists and trees, which are two different types of recursive data structure. They're important to get some practice with sooner rather than later. This was originally scheduled for another day, but now it's on Saturday. And next week there will be a midterm. Midterm 2 is on Thursday. There will be a review session held by the course staff on Tuesday at 5 p.m. in 2050 VLSB. HKN is also holding a review session that will happen this Sunday from 12 to 3 in 10 Evans. If you have a conflict with the exam, you have to let me know today. The conflict form is posted on Piazza. You are allowed to bring one two-sided sheet of handwritten notes to the exam. In addition, there will be not one but two official study guides. One of the study guides is the one that you had for midterm 1, and then there's another similar one with all the content from midterm 2, and I'll put that online probably over the weekend. The location is the same. If you want to know where the location is or other information about the exam, you can go to the course website, go down to midterm 2, click on that, and it tells you where you're supposed to go. Based on the first letter of your email address, you should either go to Dwinell or Pimentel. If you're not sure where to go to 145 Dwinell. The study guides will be linked from here. Here's a description of everything that's on the exam, which is everything we've covered in lecture, including today, but not including next Monday. And then next Wednesday, there will be no class. So today's lecture contains the last of the midterm 2 material. Monday, I'll just go over some examples. Next Wednesday, I'll just give you some time back because you have to take the exam in the evening. And then next week, there's no discussion sections either. There will be office hours Monday through Thursday. And some of those office hours will have particular themes, topics on the course that have traditionally given people some challenge. So we'll post that schedule over the weekend. If you want a little bit of extra review, we'll make sure that happens in office hours. But you can always come to the regular office hours and ask questions. I do recommend taking a practice exam at some point before the actual exam, just to give yourself a sense of how things are going to go. And if you have questions about previous exam problems, come on by. Lecture next Friday is a video, but it's a great video. So if you want to watch a video, you should come. Otherwise, watch it online. Any questions about any of this stuff? Okay, today we're going to talk about sets. Mostly I picked this example because I'd like to show you how you use linked lists and trees in order to build other abstractions and analyze their orders of growth, how long they take to compute various things. So mostly this is just a bunch of examples of how we use the ideas that we've already developed for a new application. So sets. Sets are actually a built-in data type in Python. We haven't really used them yet. The goal there is to represent what items are in some collection, but you don't care how many times those things are in the collection. You just care whether something is in the set or it's not. In order to form a set using the built-in Python set type, you enclose expressions within braces, the same curly braces that you'd use for a dictionary, but you separate all the elements by commas. Now, sets do not contain duplicates. That's their main property. They either contain an element or they don't, but you can't have the same element twice. You can't have the number 2 twice in the same set. So duplicate elements are removed on construction, and it's impossible to get duplicates in there. The other thing you should know about sets is that they're unordered. Now, what does that mean? That means there's no way to predict what order they will be printed out in when you print out a whole set. So it doesn't mean there is no order. If you write down a set, you have to write down the elements in some order. It means that order is not reliable. It's not something you should ever trust or count on when you're writing a program. So when you have a set, instead of thinking about what order things are in, just start thinking about what's in there and what's not. That's the point. Okay, so if I were to create a set in Python, I would do so by putting a bunch of numbers within braces. And here I've added 3, 2, 1, 4, and 4 to the set. If I then display the set, you'll see that it's not what I put in the first place. Well, it has all the same elements, they're just in some arbitrary order, and there's no duplicate 4. So that's the rules of the sets in action. You can't ask what's the element at index 1 of a set, because they don't have elements by index. They just either have elements or they don't. So you can ask whether 3 is in the set. So 3 is in S, that's true. You can ask the length of a set, which is how many elements are in it. Notice that it's only 4, even though when I built this set in the first place, I wrote down 5 different values. But because duplicates were removed, there's only 4 unique items in this set. Let me pause. Okay so far? Question? You're not guaranteed that it will be in order or out of order. Different versions of Python on different computers might print them out in any order they want. It does happen to be that 1, 2, 3, and 4 are in order on this particular slide, but that's not something you can rely on. So how do you get something out of a set? You can't remove it by index, but you can remove an element. So I could say, if I have a set, I could say dot remove. Let's try it. Python 3, here's my set. 3, 4, 2, oh, let's get 3 in there apparently. 2, 5, okay. There's my set. It does happen to be in order, but there's no guarantee that that will always be true. If I added some other things in here, they might show up out of order. Let's see if we can get anything to show up out of order. Yeah, so this just like scrambles it however it wants. It's totally out of control. Small integers tend to stay in order, but not on all versions of Python, so don't rely on that. Okay, and you are asking, how do I remove something? Well, I can remove the number 2 like that. You can ask whether 2 is in there or 3 is in the set. That won't remove it. That will just check that it's there. And as long as I'm typing anyway, I'll just show you what was on the slide. You can intersect one set with another set. So if I want the intersection with 4, 5, 6, 7, that will keep only the elements that are in both S and 4, 5, 6, 7. What? Intersection, sorry about that, which is 4 and 5. And you can also take the union. So if I call this T union set with 5, 6, and 7, we'll have 4 and 5 and 5 and 6 and 7 in it, but with no repeats. why do we have this in addition to lists? Well, sometimes you want to know how many unique elements there are in some long list. Put them all into a set and check the length of the set. Now you know how many unique elements there are. Sometimes you want to perform these kinds of combinations, like intersection and union. And we'd like to have a data structure that performs those effectively without having to worry about repeats showing up in the result. Okay, so that's the built-in set type. We're going to pretend it doesn't exist and go through the exercise of designing our own sets. And that'll take the rest of the lecture. Question? Yes. I don't remember its name, though. Okay, so now we're going to try to implement some abstract version of a set, which means we're going to have to pick an implementation. And we're actually going to try 3 different implementations, look at their orders of growth, and try to understand which one's better than another. Here's the things we should be able to do in any implementation of a set. We should be able to test whether some element is in the set. That's called membership testing. We should be able to take 2 sets and return a set with all of the elements that are in either the first set or the second set. That's called a union. So a union would take 1, 3, 4, and 2, 3, 5 and give us 1, 2, 3, 4, 5. I've written them all jumbly like this so that we get used to the idea that the order doesn't matter as long as we have the right elements in there. And we should be able to compute the intersection, which returns a set with any elements in set 1 and set 2 at the same time, which for this example is only the number 3. And the final operation that we'd like to support is called adjunction. When you adjoin an element and a set, you get a set that has all the elements that were in the original set and another value. So if I adjoin 1, 3, 4, and 2, I get the set with 1, 3, 4, and 2. So adjoin doesn't take 2 sets, it takes 1 set and 1 extra element. Now the thing about adjoin is that if the element is already in the set, then you should just get the same set back out that you put in. And all of these different versions, we're going to build them so that they don't change the inputs, but instead return a new set which has the elements described in these various ways. Okay, so we're going to try 3 different ways of doing this. One is just to put all of the elements in a linked list. That'll give us some practice manipulating linked lists. A set is represented by a linked list that contains no duplicate items. So not any linked list will represent a set. We have to make sure that there are never any duplicates after intersection or after union or after adjunction. So to do that, we'll first define a function that just makes our lives a little bit easier, that tells us whether S is representing an empty set. And now we're going to write a function that tells us whether it's the case that a set S contains some value V. Where here, we're going to represent a set as a linked list containing no duplicates, so S could be something like 1, 2, 3, and when we call set contains on S and 2, it should say yes, 2 is in that set. But if I passed in 4, it would say no, 4 is not in that set. Now how do we do that? Well, an empty set has no elements, so certainly V is not in an empty set. Otherwise, we can look at the first element of the set. If the first element of the set is V, we return true. Now, how is it that I have S dot first when I've been talking all this time about how sets don't have an order? That's weird, right? Are you? Okay, yeah, so the story is, it's true that the set abstraction doesn't have a reliable order. But the implementation that we're using does have some order. And since set contains is part of that implementation, it knows what implementation we're using, namely that it's a linked list, and so it's allowed to assume that this thing is a linked list which has a first element. All linked lists have that. So there's an abstraction barrier between what a set is, just some collection of stuff, and how it's implemented. Well, that's a linked list that does have an order. Okay? So you check S dot first. If it's V, that means V's in the set. Otherwise, it's not the first element, but it could be somewhere else, so we have to check the rest of the set. We can do that recursively by just saying the value of set contains SV is the same as the value of set contains S dot rest V, assuming we've made these two checks already. This is a very typical recursive structure for processing a linked list. Check if it's empty, do some stuff with the first, make a recursive call on the rest. It almost always looks like that. Okay, how long does it take in order to find whether or not a linked list is empty? It takes constant time. You just check and see if it's the same as the empty list. You don't have to go through and check all the elements. You're done after one step. How about set contains? How long does that take to run? Well, it kind of depends on where the element V is within the set. So the set has an implementation which is ordered, and you're going to check all this stuff in that order. If you find V right at the beginning, well, that was really fast. If it's not there at all, then you have to search through the entire set. This is very typical that writing down an algorithm will have a time that depends on exactly what the contents of these different values are. But there is a way in which this is a linear time or theta n operation. The sense is that if it's the case that either V is not there at all inside of S, where n is the length of S, then you have to search through the entire thing, which takes n time. Or if you assume that if V's in there, it's in some random spot, well, then you're going to search through about half the list on average. And if you do go through half the list on average, then that might take half n steps, but that's still theta n, because a half is just a constant, and we ignore constants in this order of growth notation. So the point of this is just to say that you have to search through the whole set, element by element, in order to determine whether V is in S or not. Let's do it. Okay, so here's my linked list class. If you have questions about that, just ask. I said I was going to have a function empty, which was going to simplify my code by just checking whether S is link.empty. I could do without this, but it's kind of nice. And then we wanted to write set contains, which was supposed to take a set S, a value V, check if S is empty. If so, V is not in S. Otherwise, if the first element of S is V, then certainly V is within S. In the third case, I don't know. I could write a while statement to check through all of the rest, or I could just use recursion and say, if it's not the first element, then it's either in the rest or it's not at all. Set contains S.rest and V. So if I have a linked list that starts with 3 and then has 4 and then has 5, I could ask whether this is the sort of thing that contains 3, certainly 4 is in there too, but 7 is not. Let's keep that around, that looks handy. Okay, we okay so far? Nothing too crazy. We also need to be able to adjoin a value and a set. We're going to define intersection and union in terms of this, so let's just say what it is. Adjoining a set checks to see first whether V is contained within S. If it's already there, then there's nothing to do. We'll just return the set S. Otherwise, V is not in S, so we have to build a new set, a set that starts with V and is followed by S. How long does this take to run? Any suggestions? This has only one obvious step here, and another step here, and then another step here. But set contains actually takes linear time. You have to look through the entire list in order to figure out whether V is there. And since that requires linear time, a join set requires linear time as well, where n is the size of this set. Intersect set can be implemented as follows. I take in one set, set 1, another set, set 2. I define a function that tells me whether some value V is already contained within set 2. In order to compute the intersection, I filter set 1 using this function that only keeps the elements that are also in set 2. So this corresponds exactly to the definition I said, which is the intersection is all the elements that are in set 1 and in set 2. Here's how I'd write it as a program. And filter link is a function that we wrote a few lectures ago that just returns a linked list containing all the elements for which this function in set 2 returns a true value. That's a lie. Delete it. Okay. Since you already saw this, I won't make you guess at what it is. This is n squared. Now, why is it n squared? I told you n squared occurs when you have an inner process and an outer process. So the inner process here is checking whether V is contained within set 2. That means you have to look through all elements of set 2. And how many times do you do that? Well, you do that for every element in set 1, because that's what filtering is it's going through every element of set 1 and figuring out whether or not it's in set 2. So if both of these sets have length n, then it's the case that this process takes n squared, or quadratic, time. Here's an implementation of unioning the sets. Okay, the reason why this is not simpler, like just extending one set and the other set, is because we want to make sure that we remove all repeats. So here's a program that takes two linked lists, gives you all the elements that are in both of them, but doesn't have any repeated elements. It says, I'm going to write down a function that tells me whether a value V is not contained in set 2. Then I'm going to get all of the elements in set 1 that are not in set 2 by filtering out set 1 to keep the ones that are not in set 2. Finally, I will build a new linked list that has all of the elements in set 1, not set 2, followed by all the elements in set 2. Now this is just a procedure, step by step. It tells you exactly how to compute what you want. But you can almost read it like you would describe the process in English. And sometimes using extend and filter lets you be very descriptive about the kinds of programs you're writing in this way. Question? That's a great question. So like when you build the final link in a join, why are you putting V in the front instead of somewhere else? So far, we said, I don't care about the order of the representation, so this was just the most convenient. But you wouldn't be wrong putting it at the end. It's just a little bit more difficult to put it at the end. You're kind of looking into the future, which is excellent. We're going to try to put these in order in a minute and then see that that takes a little bit more work, but at the same time gives us some advantages. Okay, this also runs in n squared for a similar reason. For every element in S set 1, I have to combine it with an element. I have to check whether it's in set 2. And so this is a nested set of processes in disguise. Filter link goes through everything in set 1 and applies set contains to that element, going through every element in set 2. Demo time. Okay, so let's complete our implementation. We're going to write a join, which takes S and V. If set contains SV, then we'll just return S. Otherwise, we'll return some combination of V and S together. This happens to be the easiest way to put them together. And then intersect set takes set 1 and set 2 and intersects them by defining a function in set 2, which takes in any value and tells us whether it's the case that set 2 contains V. Return filter link in set 2, set 1. Thank you. Okay, so backing up, whoa, link is not defined. It's true. Put that down there somewhere. Okay, so if S is 3, 4, 5, let's just remember what filter link does. It's right here. Filter link filters it out. So if I want to check only the elements that are odd, meaning that if you divide them by 2, you get 1, on S, then I should get a linked list with 3 and 5 in it, and I do. Okay, so if S is 3, 4, 5, I should be able to create the adjoining, or adjunction, which has a D in it, adjoin set S with the element 4. Adding 4 to this set gives me back the same set, because 4 is already in there. But if I add 7, then it's going to show up as part of the list. And then if later I ask, does this set, which has 7, 3, 4, and 5 in it, contain the number 4, it will tell me yes. And if it contains the other number 8, the answer is no. So I do now have a representation of sets with these basic operations in it. Can I take this set and compute its intersection with another set, like say the set S? Well, then it should just have 3, 4, and 5 in it. Intersect set has 3, 4, and 5 in it. No repeats. Questions? Okay, so this is a linked list processing function. This is a linked list processing function. This uses a linked list processing function in order to get stuff done, and filter link is one of the classic ones. The one that checks to see if S is empty already, otherwise it filters the rest of the list, and then it checks to see if it wants to keep the first element in the list as well. So everything we're doing here is kind of breaking up a linked list into the first element and the rest of the list and processing it that way. Okay, let's improve our representation. We're not gonna make any new features of this program. It's still only gonna adjoin, intersect, union. I didn't even write union, but you got the idea. And set contains. But we want them to run faster. And one way we can make them run faster is to always keep the elements in order. So proposal 2 is a set is represented by a linked list with unique elements that are ordered from least to greatest. Now that doesn't mean that sets are suddenly ordered things. In the highest level of abstraction, the one that just uses sets in order to perform computation, we assume that sets might be in any order. And we manipulate them by saying set contains, or adjoin set, or intersect set, or union set. But then, we have an abstraction barrier, and another part of our program implements set operations. And here, we're going to assume that they're in order. And we're going to assume they're in order just for the benefit of efficiency. And it's going to do things like compare elements with less than or greater than, and break things up into the first part and the rest of the list. With me? If you're not, feel free to ask a question. Okay, so different parts of my program might make different assumptions about data. This is very common with abstraction. Okay, so back to this idea. A set is represented by a linked list in order. Well, we've already seen linked lists in order. I'll give you a homework problem about how to insert the element so that it's maintained in order. But what I'd like to show you now is a clever way to take two linked lists that are both in order and compute their intersection. So I have 3, 5, 7, 8, 9. And I have 4, 5, 6, 7, 8, 9, and I want to figure out what's their intersection. If either one is empty, then the intersection is empty too, because the elements in the intersection have to be in both of the sets. Otherwise, we know that there's a first element in both of these. E1 is the smallest element in set 1. E2 is the smallest element in set 2. And we can see if they're the same. If they're the same, then we know we want that element, E1, in our result. We know we don't want it twice, so we just put it at the very beginning of the result, and then intersect the rest of set 1 and the rest of set 2. Now the important thing here is that this result is still in order. It's in order because E1 was the smallest thing in set 1 and the smallest thing in set 2. Both of those had no repeats, so all this stuff must be larger than E1. Otherwise, if E1 is less than E2, then I know that E1 is not in the intersected result. Because it's not E2, and it's smaller than E2, and everything else in set 2 is larger than E2, so E1 can't be in E2. So I return the result of intersecting set 1.rest with set 2. So this basically says, give me the result after I've thrown away set 1.first. And finally, if it's the case that E2 is less than E1, then I just intersect set 1 with set 2.rest for exactly the same reason. Question? Okay, so we want to intersect, which means we only want to keep elements that are in both sets. If E1 is less than E2, that means E1 is smaller than everything in set 2. That means it's not in set 2, so we throw away E1. This is kind of a big deal. This logic of how to take two ordered linked lists and figure out what elements they have in common. And it's kind of a big deal because it's a much more efficient process than taking every element in set 1 and comparing it against every element in set 2, which took quadratic time and squared. This actually only takes linear time. Why does it only take linear time? Well, the total length of set 1 and set 2 together is 2 times n, a linear amount. And every time we make a recursive call, we're throwing away either E1 or E2 or both of them. I mean, we don't throw them away in this case. We keep it in the result. But the point is, we make progress in either one of the lists or the other. So we're going to have, at most, a number of recursive calls that's the length of set 1 plus the length of set 2. And adding n plus n just gives you 2n, which is the same as n in orders of growth. So this is like way faster. If you have 1,000 length set 1 and 1,000 length set 2, checking every element in here against every element in there is 1,000,000 checks. This will only do 2,000 at most. But people never do this because there's an even better idea. So here's the even better idea. Sets as binary search trees. You'll study these extensively in 61B, but I'd like to show you that you have the tools to work with them already in 61A. Binary search trees are a clever way to represent a set, where you represent a set as a tree that always has exactly 2 branches. And the entries in that tree are the elements in the set. A binary search tree is a special kind of tree that has the following property. For every entry, all of the elements that are larger than that, the entry is larger than all the elements in the left branch and smaller than all the entries in the right branch. Let me show you some examples. This is a binary search tree. So 7 is bigger than everything in the left, and 7 is smaller than everything in the right. Now this property has to be true for every entry. So let's look at the number 3. 3 is smaller than 1 and bigger than 5. Has to be true of 9 as well. 9 is smaller than 11, which is its right branch. Now this isn't the only binary search tree that can hold this set of numbers. I could also draw this one, and it has the same property. Every entry is bigger than everything on its left and smaller than everything on its right. And that's true for 3 and for 7 and for 9. And it's obviously true for the leaves as well, 1, 5, and 11. There's another one. You think these are the only 3, or do you think there's more? You think there's more? If you think there's more, then you have to come up with one. And you don't think there's more? Might be more. Oh, that's an interesting idea. So it is a tree if every entry in the tree only has right branches. So at the very top would be 1, and then after that you'd have 3, and then 5, and then 7, and then 9, and then 11, and no one ever has a left branch. Well, that would be another binary search tree, a really tall one. I like really tall things. Okay, so to represent this, I'll just show you how we might do it. We'd want a class that represents binary trees. A binary tree is something that always has exactly 2 branches. That's different from our tree class that we've been using so far, which has an arbitrary number of branches. So here's how we would have a tree class with exactly 2 branches. A binary tree is a tree that has a left branch and a right branch. In order to make sure that we always have 2 branches, we're going to have to fill in the missing branches of the tree. So 9 only has a right branch, but it's supposed to always have a left branch and a right branch. We can make sure that's true by introducing an empty branch. Now this is nice because otherwise if we only had 1 branch, we couldn't tell if it was left or right. But by putting an empty branch here, we can tell. And in fact, with binary trees, it's common to put empty branches everywhere, even on the leaves, in order to make sure that every binary tree has exactly 2 branches. Let's look at the implementation. A binary tree is a special type of tree, so we can use inheritance. We have to somehow represent this empty tree. And I've just picked an arbitrary representation to say that it's a tree that has no entry. And it's one that's empty. So I've added an attribute isEmpty to the empty tree. Okay, if I were to create a binary tree, I'd like to create it from an entry and a left branch and a right branch. I'm going to do that by creating a tree with that entry and putting left and right into a sequence and passing that in. And declaring this tree is not empty because it has an entry. Let me pause. Questions? Yes, so this empty tree is special. It's the one that doesn't have branches. Everything else has exactly 2 branches. A left branch and a right branch, I could represent them as branches 0 and branches 1. Now, if I wanted to create a binary tree, I'd do it like this. I'd say, this tree has 3 as its entry, and its left branch is the binary tree with 1. And its right branch is the binary tree with 7, which has the binary tree 5 and then 9. And then in order to create 9 here, I have to explicitly say the left branch is empty and the right branch is 11. Here I've just shortened binary tree to bin using assignment. You can do that. You can give a new name to a class whenever you want. Cool. Let's write an algorithm for figuring out whether in this binary search tree an element exists. So setContains traverses the tree. It does so in the following way. If the element is not the entry at the root, then it's either in the left side or it's in the right side. You know it's not both because there's no repeats. Furthermore, you know whether it's in the left or it's in the right. You know whether it's in the left or the right because you know it's either bigger than or less than the entry. Anything that's smaller than the entry has to be in the left branch. Everything that's bigger than the entry has to be in the right branch. So searching for an element involves just following one branch instead of both. And by focusing on only one branch, you're basically throwing out half the tree each time. And that's really fast. Because if you can discard half the work each time, then you'll have quick path just to find the element that you're looking for. Okay, so here's some binary search tree. Here's the number I'm looking for, 9. What I do is I define setContains by checking first to see if S is the empty tree. If so, V is not in there. Otherwise, I check to see if the entry is V. So here is 9, 5. Well, it's not. So if it's not equal to, then it must be less than or greater than. And in this case, we can compare whether the entry is less than V. If so, then I just look into the right branch. and see if the element is there. So if 9 is anywhere in this tree, then it has to be in this branch. I haven't searched through this branch yet. I've only looked at the number 5. But I'm going to disregard everything in the left because I know that all that stuff is too small, so 9 can't be there. If, on the other hand, I was searching for a smaller number than 5, then I would only look in the left branch and not the right branch. This, again, this snippet of code is a big idea. It's an idea that if you have a bunch of numbers structured in this way, you could find whether one of those numbers is in the whole set just by traversing the tree and not having to look in all the branches, but just one at each step. Okay, what's the order of growth of this process? Well, you have to go through each branch and then check its branches and then check its branches, but you only move one direction each time, not both. So the most you'll do is the height of the tree. And in fact, for every element that's not in the tree that you have to search for, you're going to have to traverse the height of the tree. Now, the height of the tree may vary. In this case, it's always a path of 2 to get down to the leaf. But if I were to look for number 4, I would look first in the left branch, and then I would look in the right branch of 3, and I'd be done already because I see that there's no right branch of 3. And so 4 can't possibly be in this tree. So again, this is kind of an average case, assuming that the element's not in there or it's in some random place. Now, what is the height of the tree? Well, it depends. We saw a bunch of different trees for the same group of numbers. If you set it up such that the left branch and the right branch of every tree and every subtree within that tree have about the same size, then you can actually have a tree whose height is only the log of the number of elements in the tree. This is a factual study in future courses, but just to give you an intuition, if you have a height of 4 here, if you have a height of 2 here, then I can have up to 4 different leaves, or 2 to the 4th. And if I had a height of 5, I could have 32 different leaves. So the number of numbers that I can put into a tree that only has a height of n is 2 to the n leaves plus everything inside. And that means the amount that you have to search through relative to the size of the whole set is only log n. Okay, I'll show you a picture because I'm eventually going to ask you a homework problem. And when you see that homework problem, a join set on a tree, you should remember this picture. Here's how it works. If I want to add the number 8 to my tree, I'll do it by checking whether 8 is bigger than or less than 5. It's bigger than 5, so I'm going to put 8 in the right branch. The right branch is 9, and so I check whether 8 is bigger than 9. It's smaller, so I put it in the left branch. The left branch is 7, so I compare 8 to 7 and realize that 8 is bigger, and so I put 8 in the right branch. Whenever I reach an empty tree, well then I know that 8 wasn't in there already, and so I make that my new result. I then build up the entire tree set using 8 to begin with, returning that, and returning that as the right branch of the existing tree. So now the existing tree, instead of just being 7, is 7 and 8. And this is the left branch of this existing tree. So instead of having its left branch be 7, it's now 7 and 8, giving me a whole tree that starts with 9 at the root and still has the binary search tree property that 8 is to the right of 7 and 7 and 8 are both to the left of 9. And then this becomes the right branch of the result here. And so we get the entire tree with 8 in it in the correct place. Eventually, you'll be asked to write this recursive procedure. But that won't happen until after the midterm. Have a good weekend, and I'll see you on Monday.